Hey, so this is the first lecture of our unit on group theory. This material can tend to be a bit abstract, and I'm trying to present this material in a very goal-oriented fashion. The end of this is we should be able to understand how addition on an elliptic curve works for purposes of cryptography. We're just taking a bit of a detour so we can fully understand the stuff that goes into that. So to frame this next series of lectures, I want to talk about different forms of addition and multiplication that you've probably encountered in your mathematics career so far. So we have lots of different things that we all call addition. So just some very basic examples. I can add fractions together, and I know that I'll get a fraction when I say that a quarter plus 2/3 is 11/12. I can add arbitrary real numbers together, and here I've used parentheses so I can say that pi plus minus pi gives me 0. And this is sort of going to be a theme for this unit. I really do want to be using addition symbols whenever possible, so it's always the same operation. And subtraction is really just adding a negative number onto what I've already got. So I can say that subtracting 1 is really the same as 3 plus a negative 1, and that gets me a 2. And even though all three of these equations happen in the real numbers, my top equation is really happening in the set of rational numbers. I'll never get an irrational number out of this equation. And even beyond that, my bottom equation, 3 plus negative 1 equals 2, that's happening in the integers. And I know that adding integers together, I'll never end up with a proper fraction. I can get a little bit more involved with these. There's a lot more things in math that we can add together, and it's kind of a philosophical question as to whether you want to count these as the same kind of addition, right? I can add two functions together and get some new function, f of x plus g of x equals h of x. A more concrete example of that is the trig formula when I say that sine squared of x plus cosine squared of x equals 1. This is taking two different functions, and no matter what value of x, the values of these two functions added together is always going to be 1. Or you could think of the 1 on the right-hand side being a function whose value is always 1 no matter what value of x we put into the function. If you've seen linear algebra before, and I expect that you have, we can add vectors together so long as they are the same length. So here v plus u equals w. We can add matrices together so long as they have the same dimensions. So a plus b equals c, and this is assuming that all three of these are rectangular matrices of the same dimensions, which I've just sort of left off here. And then finally, the kind of addition that we've been working with in this class under modular arithmetic, here I've got 13 plus 10, and since I'm working modulo 20, 13 plus 10 is congruent to 3. And I would get a different residue there if I had a different modulus. So the actual behavior of this addition is going to change depending on what kinds of things I'm going to be adding together. I get a different answer for residues mod 20 than I would have for residues mod 21. We can play a similar game with multiplication. And my examples here are the same values as my examples for addition, but I get different results. The thing that I'm trying to emphasize here is that multiplication actually follows a lot of the same rules that addition does, even though we get different results out of these formulas. So my fractions multiply to get 1/6. My pi times negative pi gets me negative pi squared, and my 3 times negative 1 gets me -3. And you can see that I'm still staying within fractions on top. Pi times negative pi, I still get a real number, negative pi squared. 3 times negative 1, I've multiplied two integers together, I get another integer. And we can carry on multiplying in more exotic settings, so I can multiply functions the same as I've been adding functions together. A concrete example of that would be cosine of x times sine of x, cosine of x times tangent of x equals sine of x. So here I do get a recognizable function on the right-hand side. There's not really a multiplication for vectors except in 3 dimensions. You might remember the cross product, where the unit I vector cross product with the unit j vector gives us the unit k vector. But that doesn't work in general. That's just for dimension 3, or also dimension 7, but don't worry about that. I can multiply matrices together, but now instead of having this identical dimensions, they have to have dimensions which go together, right? I can multiply a 3x2 matrix against a 2x5 matrix. It's for the fact that the 2's in the dimension of the A and the dimension of the B are equal to each other. So we have a slightly different setup for when we can multiply matrices together. And finally, in modular arithmetic, we can multiply residues any way we like with some slightly unexpected results. So here I've got 13 times 10, which reduces to 10 modulo 20. This is a pretty weird behavior for modular arithmetic. We saw that cancellation does not always work in the integers mod n. Here, if I could cancel, that would be saying that 13 is equivalent to 1 modulo 20, which is not true. And again, we would get different answers for this multiplication depending on what kind of residues we multiply together. I would get a different answer for this formula if I was calculating these as residues mod 9 or residues mod 10, and so on. So the idea for group theory is that these formulas, even though they are different mathematical objects being operated on, and there's different symbols for the addition and the multiplication, these are all following certain base rules that we want for working in algebraic systems. So we always want parentheses to work. So a plus b plus c had better be the same answer no matter where I stick the parentheses in. Same thing with multiplication. I've been highlighting in all my examples, whenever I add things together or multiply them together, I get the same sort of object as I started with. Adding two real numbers together should not produce a matrix, right? Adding two functions together shouldn't get me a rational number, and so on. So the question that this raises is, what sorts of rules are universal for all sorts of mathematics, all sorts of addition, all sorts of multiplication? Let's go on for a couple more common things. If we're going into this study with the idea that we're going to be solving algebra problems, we want to have some way to undo these operations. So in addition, that'd be subtraction, and in multiplication, that would be division, and so on. And keeping the framing that I always want my plus sign or my times sign to be present, I can just pass that negative off and say that A is some number, negative A is some other number. What makes them special? Together they add up to 0. And my A here could be a number, right? It could be an integer, it could be rational, irrational. But my A could also be a vector, right? If I put my little vector hats on there, negative vectors exist. Vector A plus vector negative A will also give me 0, but that 0 will be the 0 vector. If I'm working in multiplication instead, I can do the same thing. If I want to undo multiplication, I want some A inverse, where A times A inverse gets me back to 1. Why the number 1? Because 1 times anything else should get me that other number or that other function. This was what we were talking about back in multiplication mod n, because not all elements of z mod nz are invertible. There's some residues A that do not have an inverse, like 10 modulo 20 on the previous slide. So the way we solved that at the time was we said, well, some residues do have inverses. Those are the ones that are relatively prime to the modulus n, so we'll just stick to those special residues, those invertible residues, for our applications on cryptography and random number generation. So we need to be keeping those same caveats in mind. We're trying to build up algebraic systems that behave nicely and we can actually solve problems inside of. So this is a pretty big subject. Group theory is the kind of stuff that can fill up multiple terms of coursework, and you can get very abstract. There's lots of different places you can go into with group theory. And while it is very beautiful material and very abstract material, that is not the goal of our course. So while we're treating this material, it may help to keep in mind that there's a single end goal that we have for this detour in our class. We're trying to figure out what are some more abstract versions of addition and multiplication out there so that we can understand a particular system, which is addition of points on an elliptic curve. So the same way that we have used modular arithmetic to build up a different system of addition and multiplication and exponents, our end goal for this material is being able to do the same thing for an elliptic curve. So we need this base understanding of what kinds of systems we're looking for, and in a couple weeks I'll be able to say, this is what an elliptic curve is, here is how addition of points works on the elliptic curve, see how it has the same behavior that we have been studying in the group theory section, and here's how we can put it to work towards cryptographic systems. Okay, that is a lot. So my second part of this lecture is going to be a case study on a particular group. And then finally, I will give the axioms for all groups as the final chunk of this lecture. If any of this seems like really out there, please do contact me if you need any assistance with this. And I think that rewatching these can also be helpful. All right, see you in a bit.